Hi, and welcome to 11.6 Parallel Circuits. Now that we've done series circuits, we can take a look at parallel circuits and see how are they similar, how are they different. And let's start by just talking about the concept of a parallel circuit. For parallel circuits, you'll still have like a battery and some wires, but instead of just one loop, there could be multiple paths. So this is one path that you could go through, and this is another path that you could go through. All right, so the check is if you're traveling along here with your finger, trace it with your finger, and then if you have to make a decision, do I want to go this way or this way? This is what's known as a junction. If there's a junction, then you know it's a parallel circuit. Now let's draw some resistors here because we wouldn't just have wires, we would have some resistors in each branch. So this is one branch with resistor 1, and this is another branch with resistor 2. And what can we say about these things? Well, the voltage supplied to the circuit, let's say it's a 9-volt battery. The voltage across resistor 1 from this position to this position is still 9 volts. And across resistor 2 from this position to this position, it's the same because the way the wires are oriented, you get the same potential drop. Okay? So that's why all the voltages are equal to each other in parallel circuits. So just like in series, the current was the thing that was the same. It was like a one-lane highway and everything was traveling at the same speed. Now we have the voltage drop across each thing is the same. Okay, so that's powerful information to have. And let's look at the current through each branch. So again, we have branch 1 and branch 2. Let's say the current through this is going to be 2 amps, and the current through this one is, let's say it's 4 amps. Okay, that means over here too, this is 2 amps, and over here is 4, and even over here, this would still be 4 amps. It's part of this branch. So you have 2 amps coming out of this junction, and a 4 amps coming out of the junction. So what has to be coming in to the junction over here? Well, if there's 4 and 2 coming out, there has to be 6 amps going in. That's Kirchhoff's current law, and it's basically saying that the sum of the current in the branches is equal to the current coming into the branch. It's really saying like this: if you have a multiple choice question like this, and it's 5 amps going in, another 4 amps coming in, and then they tell you, okay, there's 3 amps coming out. You'll see something like this. What does that ammeter read? Can you figure it out? Well, the first thing that you have to do is figure out how much current is going in. So going in, I see 5 amps in and 4 amps in. And then coming out, I only see 3 amps. So there's 5 plus 4. There's 9 amps coming in and 3 amps coming out. If we wanted those things to be equal to each other, what do we have to do? We have to add 6 amps. So the ammeter A must be reading 6 amps going out. Okay, so that's just like a little side thing about current and junctions that is important due to Kirchhoff's current law. So that kind of goes along with that. Voltage is the same across everything in parallel, and the current in each branch adds up. What's going on with the resistance in parallel circuits? It's kind of weird. Look at the formula. Before, for series, the resistance was pretty straightforward. It just, the more resistance you get, you add it all up and it's fine. But what happens is, because of the way the wires are oriented here, when you add another resistor in parallel, you're actually giving another path for electrons to flow. So now the electrons have this choice they could go through. There could be more current going through here. And by adding another pathway, you're allowing for more current to go through. And if there's more current, then what's going to happen to our overall or our equivalent resistance? If you look up at Ohm's law, all right, here it is. Current and resistance are inversely related. So if there's more current, what happens to the resistance? The overall resistance should go down. So does that mean by adding a third resistor, the overall resistance actually goes down? Yes, that's how it works. And let's say that each one of these is, let's say it's 2 ohms, 2 ohms, 2 ohms. Okay, and we'll use this equation to figure out what the equivalent resistance is, just as an example, because it's kind of like a, how do you handle some algebra that looks like that, right? So if we're looking for the equivalent resistance, and remember, the equivalent resistance means, okay, I want to come through here and just replace it with one resistor of an equivalent resistance to these three so that I get the same current at this position over here. This is our ammeter here, and the point is we want to have this current be the same as that current by just having one resistor instead of three. So let's do the math and figure out what is that equivalent resistance. So you're going to have 1 over R EQ is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And in this case, we made them all the same. They're each 2 ohms, we said. So you have 1 over REQ is equal to 1 over 2 plus 1 over 2 plus 1 over 2. And if you want to be fancy, you could keep it in fraction form. So let's keep it, should we keep it in fraction form? It doesn't matter. Let's just see. 1 over, so remember, this is 1 over REQ. Don't just make it REQ. 1 over REQ is equal to, well, these are all, it's a common denominator of 2, so that's convenient. So you could just add the numerator together because the denominators agree. And you get 1 plus 1 plus 1, you get 3 halves, or 1.5 you could write instead. But I'm going to keep it as 3 halves to show you how to solve here. So there's 2 choices. You could cross multiply. So 1 times 2 is 2. 3 times REQ is 3 REQ. And then you're going to divide like that. And then you get REQ is equal to 2/3 of an ohm, which is equal to 0.6 repeating ohms. So that's your answer. So that's the first way, is the cross multiply. The second way you could solve is if you have, let's say, the same thing, 1 over REQ is equal to 3 over 2. And we don't have just REQ. We have 1 over REQ. So to solve, what you could do is take the reciprocal of both sides. You flip the fraction, and you get REQ over 1, for just REQ, is equal to 2 over 3. You flip the fraction. You take the reciprocal of both sides. And look at that, 2/3, 2/3. It gives you the same thing. So if you want to think of it with fractions and try to make common denominators, and then that's convenient because at the end you're going to have to take the reciprocal. You know you're going to have to take the reciprocal because it's 1 over REQ. That's totally fine. But if you just want to plug in your calculator, 1 divided by 2 plus 1 divided by 2 plus 1 divided by 2, it'll pop out 1.5. And you could still take the reciprocal at this point because this would be equal to 1 over 1.5. And if you plug that in your calculator, you still get the 0.6 repeating answer. So there's a lot of different ways that you could be doing this, and they're all valid. But what's not valid is leaving it like this. Your answer isn't 1.5 ohms because that's equal to 1 over REQ. We want REQ, not 1 over REQ. And the EQ is the equivalent resistance, right? So that's why we do 1 over 1.5 or 0.67 ohms. That's the answer, not 1.5. So there's like a whole different set of rules that we need to remember when we're talking about parallel circuits. And the first step, and this one's going to be obvious, they're all parallel circuits for this homework. But the first step is always to identify, am I looking at a series circuit right now or parallel? So they're all parallel for this one. So let's see. Okay, so what is the total voltage across each bulb? We know from our reference table that the voltage is the same everywhere for parallel circuits. So across the 2 ohm bulb, it's 12 volts, and across the other 2 ohm bulb, it's still 12 volts. It's the same voltage everywhere, so just 12 volts. Then it says, what is the current in each branch? So if I know, let's call this 1 and 2. If I know the voltage across the first one is 12 and the resistance is 2, I could do I is equal to V over R for the first one. And the voltage is the same everywhere, so I'm just going to keep it that. So the voltage is 12 volts, and the resistance is 2 ohms for the first one. So that's 6 amps. And for the second one, V over R2, in this case, not only is the voltage the same, but because the resistance is the same, it's going to be the same math. Okay? So it's 6 amps. So there's 6 amps through the first branch, 6 amps here, and there's 6 amps here. And it says, what is the total current provided by the battery? Well, if there's 6 amps coming out of this junction here and 6 amps coming out of this junction here, then we know there must be 12 amps going into the junction right there. Okay, so it's Kirchhoff's current law again, and they mention it up above here. Okay, so the total current is going to be 6 plus 6, 12 amps. And that is also in your reference table for current. We had 6 amps for branch 1 and 6 amps for branch 2. So that's going to equal your total current, 12 amps. So if you don't like looking at the diagram and thinking about Kirchhoff's current law, it's still a relationship that's in your reference table. And now D says use the total current and the total voltage to calculate the total resistance or the equivalent resistance. So you have R is equal to V over I, and this is the equivalent resistance. We're going to use the total current, and the total voltage is the same everywhere. It's 12 volts. So this is 12 volts over the total current is 12 amps. So the equivalent resistance is 12 divided by 12. It's only 1 ohm of resistance. But how could that be? I have a 2 ohm resistor and a 2 ohm resistor. In series, 2 plus 2 is 4. But in parallel, you could say 2 plus 2 is 1. So that's the rule for parallel circuits. The equivalent resistance is always less than the smallest resistor. And we could look at the weird equation here. Does this hold true? Let's see. So this is equal to 1/2 plus 1/2. What's 1/2 plus 1/2? 1. And really 1 over REQ is equal to 1. And you take the reciprocal, REQ is still equal to 1 because 1 over 1 is 1. 1 ohm. Okay? And we talked about before, you have a path for current to go through here, and there's a whole other separate path. It's like if you have a 2-lane highway instead of a 1-lane highway. There's more space for the current to go through. So the equivalent resistance, if you could redraw this with just one resistor with 1 ohm of resistance and 12 volts here, you'd get the same current at this position and this position. It would still be 12 amps, right? Because I is equal to V over R. So it's 12 volts divided by 1 ohm. Or you could have I is equal to V over R over here, 12 volts divided by the equivalent resistance, 1 ohm, and you still get the same current. Okay, number 2 says, what is the total voltage across each bulb? So it's reminding you that, oh, the voltage is the same everywhere. So you could say like V1 equals 12 volts and V2 equals 12 volts. And this is bulb 1 and bulb 2. All right, and what is the current in each branch? So we're going to do the same thing. I1 is equal to V over R1. The voltage is the same everywhere. So it's equal to 12, equal to V. Okay. Voltage is the same everywhere, and then you get 3 ohms. So this is equal to 4 amps. And it's going to be the same because it's the same resistance. So this is 4 amps here and 4 amps here. And it says, what is the total current provided by the battery? So the I total is equal to I1 plus I2. So 4 amps plus 4 amps is equal to 8 amps. So at this position here, there's 8 amps of current. And then again, you do R is equal to V over I. The total current will give you the equivalent resistance. And you do 12 volts over the total current, 8 amps. And then you do 12 divided by 8, simplifies to 3 over 2, or 1.5 ohms. That's the equivalent resistance. Again, it's less than the smallest resistor for parallel circuits. Okay. Then we got this one. Now it's getting a little bit more interesting. We have two different resistances. So what's going to happen there? The voltage is still the same, 12 volts. From this position to this position, there's 12 volts. And from this position to this position, there's 12 volts. All right, so what's the current in each branch? Well, we'll call this the first bulb and the second bulb. So I1 is equal to V over R1, 12 volts divided by 2 ohms. So there's 6 amps of current through the first branch. And there's going to be V over R2, 12 divided by 3 ohms. So now this is 4 amps. So it's different. And is that at least what we would expect? Because there's less resistance, so there's more current. And here there's more resistance, so there's less current. So at least that makes sense. A lot of the stuff for parallel circuits is a little bit counterintuitive at first, but at least it still holds true that in each branch, given the same amount of voltage, because it's the same voltage everywhere, in each branch, the more resistance, the less current you're going to get in each branch. But you could still do the total current the same way. So the total is just I1 plus I2. You have 6 plus 4 coming out of this junction. How much is going in? 6 plus 4 equal to 10 amps. So there's 10 amps total coming into that junction. And now, again, we could find the equivalent resistance using the total current and the voltage. So Req is equal to V over I total. 12 volts divided by 10 amps. That's going to give you 1.2 ohms. And again, just to check, this is actually a check to make sure you're doing it right. The equivalent resistance should always be less than the smallest resistance. So 1.2 is less than 2 ohms. So we know we did it right. Now for this one, we have 3 different resistors. Okay, so it says what's the voltage across each resistor? 9 volts. It's just a reminder that it's the same voltage everywhere. And what is the current in each branch? So I is equal to V over R for each one. So 9 volts divided by 2, that's 4.5 amps. So there's 4.5 amps here. And then we got the second one, 9 volts divided by 3 ohms. So that's equal to 3 amps in this branch. And then the last one, 9 volts divided by 1 ohm is going to give you 9 amps in this. There's a lot of current here because there's not that much resistance and the same voltage is pushing it through. All right, 9 volts pushing through 1 ohm. So now the total current is going to be 9 plus 3, so that's 12, plus 4, that's going to be 16.5. So we have I is equal to I1 plus I2 plus I3. You plug it in, and you get the current is equal to 16.5 amps. Okay, now they're gonna. We've been finding the equivalent resistance by using the total current and the total voltage, which is a good way to do it. But now the second page is going to have you do this, which is what we started by talking about. So I'll let you pause the video and read that on your own or look at your worksheet, and let's do the work. So we're going to have to we're going to use that formula for these different things. Okay, so let's see. It says 2 8-ohm resistors in parallel. So we have 1 over Req is equal to 1 over R1 plus 1 over R2. And then we got 1 over 8 plus 1 over 8, 2 resistors in parallel. So that's equal to 2 over 8. But remember, that's 1 over Req is equal to 2 over 8. and then you take the reciprocal, or you cross multiply. Well, I guess we'll cross multiply. 2 times REQ is equal to 8, and then you do REQ is equal to 8 over 2. See how we just flipped? We end up just flipping the fraction. So you're going to have to do this a lot. I don't recommend cross multiplying. I recommend just taking the reciprocal of both sides. 1 over REQ becomes REQ over 1. You flipped it. And then 2 over 8 becomes 8 over 2. And then you get REQ is just equal to 4 ohms. So that's always going to be the last step. We take the reciprocal and then we simplify. So now we have, and I'm going to take a shortcut here because my battery's running low. So it's going to be the same thing. 1 over 12 plus 1 over 12 is equal to 2 over 12. You take the reciprocal, that's equal to 12 over 2. So it's equal to 6 ohms. REQ is equal to 6 ohms. And then a 4, so now it's going to be tricky because it's not a common denominator, but we could still do the fraction thing if you want. 1 over REQ, if you want to write, is equal to, and I'm just going to skip the first step where I write it down, 1 over 4 plus 1 over 8. And how do you do that? If you wanted to plug it in your calculator and then do 1 divided by, and then you know how you could do like the second button, and then there's actually second answer. So you plug in your calculator, 1 over 4 plus 1 over 8, and then you press enter, and then you type in 1 divided by second answer. And the answer thing is located where the negative sign is. And then that takes the reciprocal for you. And if you're doing calculator work, that's all you got to do. Keep doing that. I'm going to show you how to do the common denominator thing. So if we wanted the 4 to turn into an 8, you have to multiply this times 2 and this times 2. So 2 over 8 plus 1 over 8 is equal to 3 over 8. And then you have to do REQ is equal to 8 over 3 ohms. And you want to know what? You could leave it like that because that's fine. But if you wanted to, you could divide in your calculator and get an answer. All right, so now we have a 12 ohm resistor and a 3 ohm resistor in parallel. So we have 1 over 12 plus 1 over 3. And how are we going to make it a common denominator? We have to multiply the top and the bottom of this fraction by 4. So that's equal to 1 over 12 plus 4 over 12. So that's equal to 5 over 12. So REQ, you take the reciprocal of that, and you get 12 over 5 ohms. Now you have 3 8 ohm resistors in parallel. So you have 1 over 8 plus 1 over 8 plus 1 over 8. So that's equal to 3 over 8. REQ is equal to 8 over 3 ohms. And again, you could simplify. If you don't like the fraction, you just plug it in your calculator. I really just want to show you how easy it is if you do the reciprocal. A lot of my students kind of like the cross multiply thing because that's what they're used to. And who likes fractions, really? But it's easy once you get the hang of it. I think it's easier to just flip the fraction at the end. All right. And again, we're flipping the fraction at the end because it gives you, when you do this math, that's giving you 1 over REQ. So the last step is to take the reciprocal in order to get REQ is equal to. That's why I'm writing REQ equals instead of 1 over REQ equals. All right, that's a lot of people forget to do that when they're solving for the equivalent resistance in parallel. You got to do that last step. Okay, so 2 6 ohm resistors and a 2 ohm resistor. So 1 over 6 plus 1 over 6 plus 1 over 2. The common denominator is 6. How do you do that? You have to multiply this and this by 3. So this is 1 over 6 plus 1 over 6 plus 3 over 6. So what's 3 plus 1 plus 1? So that's 5 over 6. And then the REQ is equal to the reciprocal of that fraction, 6 over 5 ohms. All right, and then you have a 1 ohm, 2 ohm, and a 3 ohm resistor in parallel. So 1 over 1 ohm plus 1 over 2 ohms plus 1 over 3 ohms. What is the common denominator here? It's actually going to be 6. So let me space it out a little bit. So to make this denominator 6, you have to multiply by 6. And whatever you do to the bottom, you have to do to the top to make sure the fraction stays equivalent. And then to make 2 into a 6, you multiply it by 3. Whatever you do to the bottom, you have to do to the top. To make a 3 into a 6, you multiply by 2. Whatever you do to the bottom, you do to the top. And now we're going to have 6 times 1 is 6 over 6 plus 1 times 3 is 3 over 6 plus 1 times 2 is 2 over 6. Now they're all common denominators, and we could add the numerators together. 6 plus 3 plus 2, that's 11 over 6. So REQ is equal to 6 over 11 ohms. But, you know, sometimes the fraction thing is harder. So if it's easier for you to just do, okay, 1 plus 1 over 2 plus 1 over 3 in your calculator, that would work. And actually, you could do in one line, you type in 1 divided by, and then make sure you put the parentheses. And then that'll give you your answer. It'll be the same as 6 divided by 11. Okay, so that's how you do these. Now it says use the parallel circuit pictured below to answer the questions A through D. So what is the current through the 4 ohm resistor? Well, we know the voltage through the 4 ohm resistor is 12 volts. So we'll call this 1, 2, 3, 4. So I1 is equal to V over R1. The voltage is 12 volts because it's a parallel circuit, the same voltage everywhere. This is 4 ohms, so 12 divided by 4 is 3 amps. There's 3 amps in this branch. Now it says what is the equivalent resistance of the circuit. So we could do 1 over REQ is equal to 1 over 4 ohms plus 1 over 2 ohms plus 1 over 5 ohms plus 1 over 1 ohm. And if it was me, maybe I wouldn't mess with the fractions at this point. All right, maybe I would just plug it in my calculator. And then, like I said above, I would do 1 divided by second answer, like that. But we could. What's the common denominator here? That's going to be 20. So to get 4 into 20, you have to multiply by 5. And to get 2 to 20, you have to multiply by 10. And to get 5 to 20, you have to multiply by 4. And to get 1 into a 20, you have to multiply by 20. So what's 20 plus 5 plus 4? That's 29. So 39 over 20. And then REQ is equal to 20 divided by 39. And you should get an answer of 0.5128, so about 0.5 ohms, right? Because 20 over 40 would be 0.5 exactly. So this is a little bit more, 0.51, blah, blah, blah. Okay, so 0.5 ohms. Let's use that. Now C says, what is the total current supplied by the 12-volt battery? Well, you could go through, and we figured out the current through this branch already was 3 amps. If you wanted to, you could do I is equal to V over R here, 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 add all 4 of them together, and that'll give you the total current. But that seems like a lot of work for no reason. So what you did in the previous step was you found the equivalent resistance, which we said was about 0.5 ohms. And what they're asking for is the current in this position here. So it's the same, the whole point is the equivalent resistance is the same as this, and it'll lead to the same current. It's basic. You could think of it as like it's the total resistance when you add all of these resistors together. But, you know, just remember, you're not really adding them together in the traditional sense. You're adding them together in this really weird parallel circuit sense. But the point is you could still use Ohm's law. So if it's looking for the total current, you use the voltage and the equivalent resistance. So that's why we're going to do 12 volts divided by that fraction. So if you have that fraction still in your calculator, do 12 divided by second answer to get a more accurate answer, because this isn't the whole story here, 0.5, blah, blah, blah. Or if you did it in fraction form, remember, you could do 12 divided by, parentheses, 20 divided by 39. And it'll give you an answer of 23.4 amps. And remember, I did that because I didn't round in my calculator. I left the big long decimal. Okay, so yeah, 12 divided by 0.5. That should be 24 amps, Mr. Nangle. What the heck? All right, but that's because in my calculator, I left the big long fraction, the big long decimal, and it gave me that answer instead. 24 amps is fine, though. If you want to round it, that's fine. So now it says how much power is dissipated in the 5 ohm resistor. You have to look at what we have. So the voltage is 12 volts. The resistance is 5 ohms. Could we find the current at this point? Yes, we could. But they're just looking for the power. So if you feel like finding the current, you can. But if you're looking for the power and you have the voltage and the resistance, and we actually don't care about the current, which equation should we use? So we're looking for a power equation that doesn't have current in it. This one has current, can't use it. This one has current, can't use it. Let's use V squared over R to find the power. So we got P is equal to V squared over R. That's equal to 12 squared over 5. So you get 144 divided by 5, weird looking 5. So the power is equal to 28.8 watts. Okay, and that's about it for parallel circuits. Please let me know if you have any questions, and have a great day.